Good evening and welcome to this 2019 Distinguished Faculty Lecture. My name is Billy Clow. I'm the Interim Provost and Academic Vice President, and I'm really happy to see you all here tonight. This is just one of those events that I was saying earlier. It's just great when we have the opportunity to celebrate why we all got into this business in the first place. Great teaching and great scholarship and great learning. So I thank all of the distinguished winners who are out here tonight. We'll recognize everybody in a second, but it's just a wonderful opportunity to celebrate with our students and our faculty and peers and colleagues. And so thank you all for being here and being a part of this evening. So the faculty lecture has a proud tradition dating from 1969 when President John Bernard established an award to annually recognize faculty members. In 1998, President Donald Spencer accepted the recommendation of the Faculty Senate to reconstitute the award as a Distinguished Faculty Lecturer. This year's recipient is Dr. Kishor Kapale, Interim Chair and Professor in the Department of Physics. At this time, I would like to recognize past recipients of the Distinguished Faculty Lecture Award who are with us this evening. So please stand as I call your name and remain standing, and then when we get to the end, we'll applaud for everybody. So, Mr. Nicholas Payno, Dr. Sterling Kernick, Dr. Tom Dunstan, Mr. William Makestad, Mr. Fred Jones, there he is. So, Dr. George Hopkins, Dr. Polly Radish, Dr. T.K. Vinod, and Dr. Chris Sutton. Thank you all. I would now like to thank the members of the Distinguished Faculty Lecture Committee. Would the members who are here in attendance call as I stand your name? Dr. Chandra Amravarty, Dr. Jeff Brown, Dr. Bill Knox, Mr. William Makestad, Dr. Sandy McFadden, Dr. Chris Merritt, and Dr. Catherine Polilko. So thanks to all of them who couldn't be here this evening and those of you that are here. At this time, I would like to invite Dr. Sue Martinelli Fernandez, Dean of the College of Arts and Sciences, on stage to introduce Dr. Kishor Kapale, the 2019 Distinguished Faculty Lecturer.
Good evening. Dr. Kishor Kapale is currently serving as interim chair as well as professor and graduate coordinator in the Department of Physics in the College of Arts and Sciences. Prior to joining our faculty in the fall of 2007, Dr. Kapale held a prestigious National Research Council Research Associate position at NASA's Jet Propulsion Laboratory at the California Institute of Technology after a short postdoctoral appointment at Princeton University. Dr. Kapale received his PhD in physics with an emphasis in theoretical quantum optics from the Texas A&M University in December 2002. His thesis research was centered on developing a fundamental theoretical understanding of the new state of ultra-cold matter that is termed as Bose-Einstein condensate. Dr. Kapale currently conducts research in the area of quantum optics, which involves the study of interaction between light and matter at the microscopic level, and quantum information science, which is a new paradigm in information processing for the development of better, faster, and more secure quantum computers and quantum technologies. Dr. Kapale is also interested in developing quantum sensors using the techniques of quantum optics. Sensors are an important component of modern robots and artificial intelligence systems. Quantum sensors are useful for navigation for planes, satellites, and spacecrafts with higher precision than currently possible, are useful for geological exploration, and in general, all kinds of sensing of our physical environment at an unprecedented accuracy and precision. Recently, Dr. Kapale has been interested in the theoretical development of ultra-high resolution optical microscopes for unobtrusive imaging of live biological samples. A number of quantum tricks, some of them developed by Kishor, may one day allow us to take HD videos of biology in action and not just understand how biochemical processes work, but also allow development of cures for several diseases. To his credit, Dr. Kapale has more than 40 publications in international journals that enjoy close to 1,300 citations according to Google Scholar. He has also delivered more than 85 invited talks, seminars, and colloquia. Dr. Kapale's recent research in the area of super resolution has been recognized and featured in the American Physical Society's weekly publication spotlighting exceptional physics research. Kishor was co-founder of the Graduate Research Conference at WIU, and since 2015 has served as the lead organizer of the Graduate Research Conference, which provides WIU graduate students the opportunity to showcase their scholarly, creative, and professional work, as well as hone their presentation skills. Dr. Kapale has served on numerous department, college, and university committees. He is also committed to educating our youth in STEM disciplines. With the help of several university colleagues and his wife, Aparna, Dr. Kapale is managing and coaching First Lego League Junior and First Lego League teams. He was awarded the College of Arts and Sciences 2017 Service Award, and in 2018 received Sitter's Best in Track Award in Professional Research and Creative Activities. Also, I would be most remiss if I did not say hello to Kishor's wife, Aparna, and their sons, Atarva, 10, and Apurva, 6, who are attending tonight's lecture. Hello. Where are you? There you are. Hi. Finally, I have some gossip about Dr. Kapale. He has recently ventured into artistic endeavors, including teaching himself classical guitar and appearing as the character of the prince in the local production of the ballet Nutcracker. Congratulations to Kishor Kapale, and I look forward to an outstanding lecture this evening. Thank you.
Okay. Thank you, President Thomas, Provost Clow, and the Distinguished Faculty Lecturer Selection Committee, and the past distinguished faculty lecturers for your presence, and all of you in the audience for your presence as well. Thank you very much, Dean Sue, for that very, very flattering introduction. I am extremely honored and humbled by this opportunity to talk to you about quantum physics. Even practicing scientists are still figuring out what it all means. So that means it is a tall order to give you a lecture about quantum physics in just one lecture. A warning coming at the outset, even though the title says a stroll, which is supposed to be a leisurely activity, this is going to be a thrill-filled roller coaster ride in a theme park and not a leisurely stroll. So I hope you are all okay with that. So let's move on. First, I consider delivering this lecture as a special responsibility, also because I happen to be the first lucky physicist on the WIU campus to get this opportunity to talk about my research. Physics normally gets two kinds of reactions that are normally very poles apart, extremes from people on the street. Some people love it, some people hate it, and that perception originates because physics is often closely associated with mathematics, which is what brings the difficulty in the understanding. However, it is important to note that physics is an experimental science. To note, there is no mathematics in today's lecture, so I will try to keep things simple for you. But make no mistake, mathematics of quantum physics, which I get to practice every day, is very beautiful in its own right, and I'm here to talk about the physics of it mainly. So let's take a look at what physics means, a dictionary definition of physics, if you will. It's a noun. It says physics is a branch of science which is concerned with the nature and properties of matter and energy. The subject matter of physics, distinguished from that of chemistry and biology, includes mechanics, heat, light, and other radiation, sound, electricity, magnetism, and the structure of matter, which, at the heart of it are atoms. So it actually goes even beyond that. Because I'm a physicist, I get to criticize the dictionary definition or elaborate more on it, if you will. It really deals with the interrelations between matter and energy, and also deals with subatomic physics, which they kind of missed over here. Physics forms the basis of understanding as we as humans have developed about chemistry and even biology. And I'll try to give you a little bit of a flavor of where quantum physics comes into that picture. It has provided all the measurement tools that all of these fields use. In fact, there are branches of disciplines such as chemical physics, biological physics, that go deeper into these connections of physics with other disciplines. Physics forms the basis of all branches of engineering, and it would not be incorrect or even an understatement to say that all of engineering originated from physics. So physicists on their daily day-to-day work do a lot of engineering, technology creation, and mathematics. And I happen to do that as well as I get chance to play with these things. So my goal today is to take you a little bit beyond this traditionally understood corrections. I didn't say anything new here so far. My goal today is to connect physics to information science. We live in a technologically advanced world, and information plays a huge role in that. And so physics essentially is, if you think about it carefully, it happens to be the information science of the universe that we live in. Measurement of the universe and making sense of those measurements from the results that we get to learn about the universe is what physics is all about. For good or bad, it was only within the last 2 or 3 decades that we have taken this connection very seriously and started investigating that direction, and that too with the help of and the peculiarities of quantum physics. So that's kind of my motivation to talk to you about quantum physics. So a little bit of advertisement for quantum physics, if you will. Quantum physics, which is a bit more than 100 years old, and it has allowed us to understand how stars emit light, how the semiconductor devices that power all of our computers, smartphones, tablets, etc. Work, chemistry and all of its cool applications. We haven't been able to reach that understanding without quantum physics, harnessing solar energy using photovoltaics, new highly efficient and cooler light sources such as LEDs, superconductivity and the promise that it brings of maglev trains and lossless transmission of electricity, nuclear energy, and that's kind of the quantum revolution 1, if you will. I'm going to take you to the next level, which is here. Humans themselves, our neural circuitry and memory is thought to be based on quantum concepts, a concept of entanglement, which I will try to illustrate for you today. There's a sci-fi series on Amazon, and that's where I got those pictures from. They actually even have Humans 2.0, if you will. And last but not the least, magnetic navigation used by birds seems to be based also on quantum entanglement, which we will learn later today. The last 2 parts of the pictures here are so-called the second quantum revolution, if you will, and that's what I'm here to talk to you about. Size scales at which quantum effects become important are typically very, very small. We will start with the scale of atoms, 20 times the trillionth of a meter. A meter is about yay big. trillionth of a meter, so very, very tiny, nothing that our eyes can see, for example, but quantum physics is needed to understand even what goes on inside of the atom, so-called subatomic physics, but we will not go there today. We have a large length scale to cover from trillionth of a meter to a millionth of a meter. That's about a factor of 1,000,000, one followed by about 6 zeros in size, which covers atoms, DNA molecules, to the one that Dean Su talked about, Bose-Einstein condensate, that got up on the magazine cover for Science magazine in 1995 as the molecule of the year, which is essentially a Bose-Einstein condensate. Pretty large system, about 1,000 to million atoms. And so even with this large system, it behaves on these, or follows the quantum idea. So we're going to have my trusted assistant, Jake Lambert, a graduate student in the physics department, to help us with this little demo of something that's even on a larger scale, something that our eyes can see. And so since we're talking about size scale, it is interesting to look at something that happens with the ordinary distance scale, but what we need for it to work is really, really low temperatures. And we have liquid nitrogen here, so let me put on my goggles, and let's have some more in there. Okay. Jake? So for now, if you can see it, let me switch to the camera so you could see what's happening. Okay, you could see a magnet, a really powerful magnet at the center, and we have a little disk that's sitting on top, if you could see that. Right now, it's not doing anything interesting. It's just sitting there and not particularly attracted to the magnet. Doesn't really do anything interesting. So let's now take that one out, and let's pull out one of the colder samples that Jake is going to put on there, and try to pay attention. Okay, that flew away. Okay, let's try that again. So right now you don't see anything except for a fuming little disk there. It's fuming because it was in liquid nitrogen and it got heated up very quickly as we pulled it out. I'm going to try this now, so pay attention. It was floating there for a little bit. Did you get to see that? Okay, so that it was floating on there. I think that's enough. Thank you, Jake. So what we had was, when we had the first sample there, that was not cooled to the liquid nitrogen temperature, so very, very cold. It did not do anything interesting. But the moment I cooled it down by putting it in the liquid nitrogen for sufficient time, then we got it to float. So what was going on? Why is it microscopic and why is it quantum? So it turns out it's a ceramic disk of something called a yttrium barium copper oxide, which is at those low temperatures. Okay, so there is one little trick that I need to use here, so where you can see on the screen. Okay. So we had these two samples. The behavior that you saw at low temperature is called superconductivity. And the reason why it happens is it's a quantum phenomena again. It allows that little ceramic disk to support electric currents without any losses the moment it's cooled. And when you put it on the magnet, it actually creates a magnetic field of its own, which then cancels the magnetic field of that huge magnet that we had sitting there, and then it can support its own weight because of this repulsive forces between the two systems there. And so that is basically magnetic levitation. So if you want to look up more information on it, look up Meissner effect. And I would like to thank Jake, of course, for helping me with that demo. And the samples that I used were prepared by two of our faculty, Dr. Malur and Dr. Babu. They're over there in the audience. I can see them. It took them about 2 days to get those samples ready for me. Okay, so welcome to Quantum Land. Buckle up and be ready for an exciting ride. And because we have some little kids here in the audience, think of yourself as getting into Cat in the Hat, if you know the character. Cat in the Hat's little vehicle called Thingamajigger, and there's a little button on there that when you press, you shrink. So you're going to all be shrinking down to the size of the atoms, and then let's see what we observe when we enter this quantum land. So the rules that you have to follow and the warnings to have a successful and safe ride through this theme park: don't interact with strangers, you may lose your state. Everything is going to look a little fuzzy. Everything is on the run or climbing up or down. Okay, we will explain all of these things in a little bit details because there are lots of stairs and steps. Everyone looks exactly the same, except each one of them has a little pointy stick that they're carrying, which is either pointed up, kind of like a spear, pointed up, or pointed down. And when you're looking at them, if you tilt your head, it appears that the sticks are also tilting with you. So on the top right there, I have a little picture of a historic landmark in India called Stepwell, and there are lots of steps that you can see. It's an ancient method of collecting little rainwater that region receives. Again, very nice place to socialize and stay cool in the summertime. And another kind of rule that comes here at the end is you will always need to be on the run. Now, that may seem tiring, right, when you're getting in there. But the interesting thing is you don't need any energy to run if you're on a level surface, let's say, and you won't get tired. To climb up the stairs, you need to grab a light flash that's coming at you, and that needs to have the appropriate energy. If it's not the appropriate energy, you don't get to do anything with it. If you climb down, you throw a flash of light based on how many steps you're going to jump down. Okay, so weird things going on. Some denizens that that you can see in the park happen to be of weird forms. They are mixtures of two or more forms based on what you're looking at. And some of these denizens are going to be, even though they may be far away from each other, kind of like family members. Even when you're far away from each other, you know something about what the other one is doing. And so they seem to be strangely connected to each other. So are you ready for the ride? Okay, let's go on. Let's move on now. So we will take a look at these things that I talked about in more technical details, the so-called quantum land rules. In classical reality, which is really governed by Newton's laws of motion, and I will have these yellow stamps every once in a while. Those are for the people in the audience. If you want to look up more information on it, you can pay attention to those phrases, note them down, and you can read more about it, or you can ask me questions later on. So in classical reality, which is really governed by the Newton's laws of motion, which are at the heart of our industrial revolution and the space exploration, it is completely crisp and clear, crystal clear. For example, we are able to throw a dart at a moving target, which is this International Space Station, 254 miles away from Earth. It is, as the picture shows, and if you have heard in the news, the SpaceX Crew Dragon just docked with the International Space Station earlier this month. So classical reality allows us to do these kinds of things. Quantum world, on the other hand, is a bit fuzzy. It's inherently fuzzy. Things are moving very fast. In our classical world, if you try to take a picture of them with your cell phone, cell phone pictures are always pretty fuzzy. And that's because of the technological limitations there, not because the classical world is fuzzy. There is always room for improvement in the classical world. So let's take a look at a little cartoon here at home with the Heisenbergs. Here's a challenge faced by the Heisenberg family. Mrs. Heisenberg says she can't find her car keys, and Mr. Heisenberg says you probably know too much about their momentum. So what is momentum? Momentum is just a product of the mass of the object and the speed. So it's in some sense a measure of just how fast things are moving. So this cartoon is really about, talking about something that we call Heisenberg's uncertainty relation. You cannot know a location of an object, a quantum object, as well as its speed at the same time with sufficient amount of accuracy. There is always inherent error associated with that sort of a measurement. And measuring one affects the other. So you can't really get out of this jinx, if you will. We're not talking about human errors in the measurement here. There are always that. When you work in the lab as a student, there are always going to be human errors in the instruments that you use. But this is a fundamental limitation of these quantum systems. No matter how advanced your technology is, you can't go about overcoming that. So jokes apart, quantum particles cannot be stationary at a given position. That's why I said you always need to be on the run when you're in this quantum world, as that would mean you would have a definite value for the speed that's equal to 0. And so we can't know both the position and location of quantum objects. Okay, so let's move on. Another little feature, if you will, of quantum systems. Energy comes in indivisible packets. Now, discrete things are not very arcane to us, even in our classical world. Musical notes, doesn't matter which instrument you use, they come in certain chunks, and you don't have, for example, any frequencies in between E and F. The classical world allows it, but when you talk about musical notes, standing waves created on strings, for example, by the string quartet here earlier on, they come in discrete chunks, discrete bunches, if you will. In the same fashion, if you climb a little ladder, you're safe when you're on one of the rungs, not in between. You don't want to be in between, right? And the funny thing here, a little ironic, that this particular product is called Little Giant Quantum Ladder. That's actual product name, if you will. Another example, say when you take elevator to go on the Willis Tower, say you want to visit the sky deck, for example, you hope that the elevator doesn't stop between the two floors, right? That's in this kind of the same manner, electron in an atom has a quantum ladder of energy. Only certain specific energy values are allowed, nothing in between. And if the electron, just like the elevator in any building, randomly trekking between floors, electron in an atom can do that. And to be able to do that, it needs to absorb precise amounts of energy in the form of light. And that's where light-matter interaction, which is sort of my area of expertise, that comes in. Another interesting thing is when energy from the light is absorbed by the electron, it cannot be broken up. It either has to absorb all of it or none of it. Okay? And so think about it this way. You owe some money to your friend, and the smallest denomination that you have is like $5. But you owe only $2. Now, you can't tear that $5 bill 2/5 of the way and give it to your friend and declare the transaction done. That doesn't work. You have to look up for the lower denomination. And that's kind of what it means to understand that energy sort of comes in these indivisible packets. So let's talk about it. Let's see what it really means. So if we were in the quantum world, and if I say just one small word to you, right now whatever I'm seeing, is everybody able to hear? Even in the back, right? So you all can hear. So the same sound wave that I'm making is reaching all of your ears. In the quantum world, it doesn't work that way. If I say a word, only one of you is going to be able to hear. The rest of you are not going to be able to hear anything, right? Then I would quickly lose all of you as audience, right? Not something that we can wrap our heads around easily. Let's take a look at one other example. If you like surfing, I spent some time in Southern California, so surfing is a little bit interesting. When you go surfing with your friends, the wave is experienced by only one of the several 50 or 100 people that would be there to enjoy the surf. That would be weird again. So that's just trying to connect how the quantum world is weird. There is another aspect of the quantum world. Since we are talking about energy, we need to understand how energy moves through space, how it goes from one place to the other. There are two modes of energy transfer. One is a wave, and the other one is particles. Particles have mass, position. You can figure out where they are, their momentum. Kind of like marbles or gold balls. If I throw one at one of you, when you catch it, you absorb all of its energy. Or when I drop it on the floor, all of its energy is going to do something interesting there. Waves, on the other hand, are more spread out. The energy is not localized. And to kind of visually think about the waves, think about waves on the surface of a pond when you drop a little pebble in there. Okay? So it turns out the process of absorption of energy and emission, that happens with these energy packets. You cannot really break them apart, like I already said. And Albert Einstein got his Nobel Prize in physics for developing his early theory of how light and matter interact. You may be familiar with Einstein's work on his theories of relativity, but the work that he got Nobel Prize for was the interaction of light and matter, which is at the heart of what we are looking at today. So let me show you a little simulation here of a light, the wave that's propagating. It is propagating this in this direction, along x. And if you look at this little e here, which is the electric field, the red part is the magnetic field, and you can kind of see the waves. They're moving forward. The electric field is just going up and down, and we call that polarization, and we're going to be using polarization a little later on. So the interesting thing actually happens when you start adding waves. So here is a little demo of little illustration of what the addition of waves is going to look like. Normally, ordinary numbers, when you add them, 2 plus 2, what is it? Anybody? 4, right? Everybody agrees. Even my little ones will probably agree with that, right? It does not work like that for waves. If you have waves of amplitude 2, and what I mean by amplitude is essentially half of the height that you see of these little wiggly lines that I have drawn there, then they add up to, sometimes they add up, if they're just, their peaks are matching perfectly and valleys are matching perfectly, you add them up, you get a larger wave. That is 2 plus 2 equal to 4, but not always. When the peaks are just overlapped correctly with the valleys of the another wave that's coming in, then you get complete cancellation. So you can get 2 plus 2 equal to 0 when we are talking about waves. And so here's a little illustration, and I'm going to do a little demo for you here in a moment. So you have a light source that is generating light, passing through a screen that had just 2 holes, and so I create now 2 waves that are coming in. They're going to fall on the screen, and depending on how much distance each wave has traveled, it's going to have slightly different starting point, whether it's at a peak or a valley or somewhere in between, depends on how much distance it travels. So now can we have the lights off? Okay. So I have these two. I have a laser light, pretty bright one. And if I can get this one to go away. Okay, so sorry for that, but brace your eyes. We are going to try to illustrate that interference for you. 2 openings. So without anything, just the laser light by itself creates that pretty bright point on the screen. It's a green laser light, so I'm able to show it to the whole room. And when I pass it through 2 openings, I get this dark and bright region. It spreads out throughout the whole screen. Can we have the lights back again? Brace your eyes. Okay, it does that very nicely and slowly, so that's good. Okay, so you saw how light behaves when you have addition of 2 waves. That is called interference of waves, and it's this interference that is going to be very useful for us to understand what's going on. So if you do this at the, hold on just a second. Okay, we did that. So we had these waves, for light contain millions and millions of photons. Things start getting interesting if I could reduce the intensity of my laser light and have maybe just 1 photon coming in at a time. And there we get very interesting. So for classical particles, think about a shooter that you have that's shooting tennis balls at you. And then you have 2 openings. The tennis balls are going through those openings. And let's say there is a screen behind where these tennis balls can be stuck together. You're going to get just 2 bunches. No dark and bright fringes that we saw earlier. In the quantum domain, however, if you have quantum particles that are going through it, it turns out even when you have just a single particle in your apparatus, you get these wave pattern. And that is something that is a little bit weird to understand. So let's see if that really works. And I have a little simulation here to illustrate that for you. Okay? So you saw initially there was no pattern. It's going to scroll through and loop through it again. Initially, no pattern, sort of random locations at which these photons fall on the screen, and we're going to just make a dark point there. With time, when you collected enough photons, you get these very interesting patterns back, same patterns that you would get with a very bright laser like this one here. Okay? So what's going on here? That sort of tells you that it's the interference that we saw is not because I had millions of photons shining on the screen. It is the one individual particle interfering with itself. It is mixing these two waves coming in. So particle by itself shows its wave nature when it sees this. And that means somehow when a particle is passing through these two openings, it doesn't really know which path it is following. And so it is exciting both of these modes here. You have two wave modes coming in, and they're mixing to give you these fringes. So to really make sense of what's going on here, can we watch the particles as they're going through one of these slits? And it turns out this experiment is very difficult to set up, but it has been done. Various versions of these have been done. It leads to something called a which path information. And it turns out if you know which path the particle went through, then there is really no wave character remaining. It's not a smeared nature that we have kind of washed out. We know particle passed through this one or that part, then the interference pattern is washed out, and you lose that interesting looking pattern that we had. This type of experiment is called the Young's double slit experiment. Very interesting implications. Has not been done just with photons, but individual particles like electrons, or even DNA molecules. They have been able to do this. So DNA molecules, again, we talked about it. Large size system, lots of atoms in there, can show you these interesting interference experiments. So let's now take a look at let's see what it really means, right? So this missed photon, now we're talking about the single particle. Remember, even the single particle eventually gives you that interference pattern. So she is kind of confused, misoriented. She doesn't know which path she's passing through. So in some sense, she is in a sort of a schizophrenic state, whether I'm going through this door or that door, I don't really know, but I get to the screen somehow. The second picture that you have here is a little optical illusion for you. I love optical illusions. If you look at this as if it's at the bottom corner of a room, then you could see 1, 2, 3, 4, 5, and 6 screens, right? 6 cubes, rather. Or if you look at it as if it's the top corner of a room, then you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So is it 6 cubes or is it 10 cubes? It is our mind that decides spontaneously which one to fixate on, and then you like that one. You may have seen some other pictures like that, where there is a beautiful lady and an old lady in the same picture. It's what you fixate on is something. There's nothing quantum about that, but that's the best I can do to tell you about this quantum schizophrenia, or technically what it is called quantum superpositions. So let's now look at what we can do with these superposition sort of states that have two simultaneous identities, if you will, right? That's why the word schizophrenia. In the classical world, an entity that can take two identities, either 1 or 0, on or off of a switch, is called a bit, and I'm sure all of you know that is what our standard computers are based on. Even your smartphones use classical bit as the fundamental unit of information to carry out the amazing thing that it does for us. What I have here in the quantum domain, a two-state system, can be now in simultaneous state of being either 0 or 1. You don't know which one unless you do the measurement on it. And there is a certain probability associated with this. So these numbers A and B that are coming in front of these weird-looking symbols, these are, by the way, called, they're due to a British physicist called Paul Dirac, and they're just a way to signify a quantum state of a system. So 0 is like off state of a switch, and 1 is like on state of a switch. and A and B are called probability amplitudes. So they don't quite tell you the probability of being in the state 0. Square of that, to be simplistic, is what gives you the probability. So interesting thing to note is the simultaneous existence of this quantum system in these two realities at the same time. If you have now multiple systems, you can then have them in multiple realities at the same time, and that gives tremendous amount of advantage when you apply it to information processing. It is sort of like parallel computers that you have talked about, but even more interesting and intriguing. Using that, putting it to practical use, is not a cakewalk by any means. Very, very difficult things to do. So what sort of systems can we do this in? So these are called qubits, or call them quantum coins, if you will. You know, coin has two sides, heads or tails. Quantum coins, unless you measure them, you don't know what state they are in. So it's kind of like having a coin. I have a little penny here, pretty big one, and it's kind of just spinning until I measure it. Until it falls down, I don't know whether it's heads or tails. So think about that spinning coin, if you will, when I talk about quantum coins. So here's some examples of quantum coins. Quantum dots, your TVs that you're using these days. In 3-4 years' time, you know, they may start using quantum dots as the primary light source. So very interesting quantum systems. You have about 7 little pictures here, bright dots. Those are actually trapped ions sitting side by side. You can use photons, and I will try to demonstrate some little interesting properties of photons to you. Laser beams, you know, that I'm using, for example. That's kind of what it is. You have laser-cooled atoms, which is what leads to eventually Bose-Einstein condensate. So you have 6 laser beams trying to cool a little cloud of about 1,000 atoms, if you will. Or if you take diamond, all of you know diamonds, right? The diamonds are essentially just carbon atoms. It's a molecule, a huge molecule consisting of only carbon atoms. If you remove one of that carbon atoms and replace it with nitrogen, it now creates this interesting 2-state quantum coin that you can use. And here is a picture coming from a Rigetti Corporation, a young startup, if you will. They have created an 8-qubit quantum processor. So I don't know if you have followed the classical computing trajectory. Early computers were like 8-qubit, 8-bit systems, for example. Right now, even a small laptop that you can buy from Walmart is 64-bit processor. So you just need only 64 bits for your main processing unit. Quantum systems are not there yet. We have gone to about 20 of these bits side by side. And the understanding is that if you can get 50 of these quantum systems side by side interacting with each other, then you would be able to do everything that our classical computers can do, but a lot better, a lot differently, and a lot more interesting. Okay, so these are our experimental systems. Talking about that quantum coin, you want to be, you know, like I said, that spinning coin, little penny that I showed you, only when you make a measurement on it, then you know what state it is in. So it's the measurement part that is very interesting. And for a classical system, of course, the measurement is very easy. We hardly ever do any kind of a damage to a system that we are trying to measure. It's very easy to tell apples from oranges. And remember one of the quantum land rules that I told you about? Everybody looks the same. In quantum world, you can't tell one from the other. Very difficult to do because you need multitude of measurements. So you need multiple copies to really figure out what's going on. You know, just kind of like, you know, when you are talking to a person, you want to know that person really well. You just asking one question doesn't really do it. You have to ask lots of things, lots of questions, interact with them, and that's kind of what it is about quantum system. One single measurement is actually going to change that quantum system, so you lost your opportunity to even know what that quantum system is the moment you do that measurement. One needs multitude of measurements on similarly prepared systems. So there is a huge amount of challenge that it brings, and we need to devise very clever measurement strategies to make use of this parallelism that I talked about, to make use of quantum superpositions and really take advantage of all of that. So now I'm going to show you light is one thing that we all experience every day, and it happens to have these quantum properties that are fairly easy to demonstrate. And I'm going to take a look at measurement. I'm trying to show you how you can see here how measurement affects quantum systems. So here's just a simple cartoon of something called a non-polarized wave. If you remember the little simulation of a light wave that I showed you, there the electric field was just oscillating in one direction, up and down. Normally, a light that you get from any ordinary light source, it doesn't have that very fixed direction for the electric field oscillation. It has all possible directions, so it's called unpolarized light. And if you have used polarized sunglasses, then you know it is basically filtering out some of these polarizations and allowing only a small portion of them, and you get a polarized wave, which now is much less intensity, and so that removes the glare, and your polarized sunglasses are very useful for you. Another thing to notice here is this polarizer has a certain axis, and the axis over there for the other polarizer that I have at the other end is crossed. This is vertical, that is horizontal. And when that happens, when they're cross-polarized, no light intensity passes through that. So let me get my lamp on over here, and then we can get the lights off again on that end. And I will switch over to this little picture here. So we have a little Elmo and a light. And once we have the light intensity going down, you will see what this really allows us to do. So I don't have 3 sunglasses. That would be very difficult to set up to show you what's going on. So I have 1, 2, and 3 polarizing sheets here, which basically behave like your sunglasses. So you could do this. If you had 3 sunglasses, you could do this at home. Okay, so I have 1 polarizing sheet. You can see it gets slightly dimmer, so some of the light is going away. If I have another polarizing sheet in the same direction, I don't see anything particularly interesting happening. Just slight drop in the intensity, 1 sheet here versus 2 sheets, because some of it is going to get absorbed by these polarizing sheets. If I add 3 sheets here, 1, 2, and 3, again, slight more drop in the intensity, so nothing remarkable. Let's do now cross-polarization. So I have certain axis for the first one. I put the second one at 90 degrees, and you can see all of the light that's falling on it is completely blocked. Okay? That's not, that is very interesting by itself, but not something that I want to show you. So I'm going to change it a little bit. I changed the orientation a little bit. So you have 2 sheets here. And now let me add in another sheet in between at a specific angle. Okay, and then I will show you what I have done. So that's my bottom sheet. This is the second sheet that I had added. And in between the two, I added the third sheet here. Okay, so over here, light is passing through 3 sheets. And over here, where it's a little darker, light is only passing through 2 sheets. So remember, these are polarizing filters. Filter is supposed to take away light. And here, I hope this is clearly visible to you, is that light passing through 2 sheets is actually it's much darker than light passing through 3 sheets. More light is passing through 3 sheets. Okay, so that's a little intriguing. Let's have the lights back on, and then I can explain to you what was going on there. What you saw there was quantum measurement in action. Okay, so let's talk about it, what was going on there. I need to switch. Okay, there we go. So we played with polarizing filters. What was happening there? Filter, by definition, is supposed to reduce what goes in. But what happens there is that 2 filters did worse than 3. You got more light passing through 3 filters. So why was that? That cannot happen unless the middle filter that I introduced in between was somehow changing the state of the system that was passing through. And that is basically something called a projective quantum measurement. You saw quantum measurement in action, and when you are measuring a quantum system, you invariably change its state, and then multiple measurements coming afterwards, you don't get any new information out of it because the change has happened once. if there was no change in that system as we were measuring it, if I add about 10 or 20 sheets like that, you should just continuously start seeing intensity change. And so that's quantum measurement in action for you. Let's now see what we can do with this. So we talked about some weird properties of the quantum system so far, how strange the process of measurement is. You can then naturally wonder, if all of this is so complex and weird and not easy to understand, is it even possible to put it to use? Right? And of course, I would not be here if the answer was not yes. So let's take a look at two examples very quickly of what we can do with this. Right? So you want one of the first one is secret communication. That is something that has been the need of humankind since ages. You do not want anybody finding out, let's say when you log into your bank's website, you want that communication very secret. Currently, the bank communication uses something called the RSA, last names of three people who invented this idea, RSA crypto system, which basically relies on our mathematical inability to factor very, very large integers. And even computers, we don't have even efficient computer algorithms to do that. So even computer cannot break that security, for example. If we were to build quantum computers, they could break that security. But that's not what I'm going to talk to you about. I'm going to tell you a quantum method to ensure this secure communication. So here's a little cartoon here with Alice and Bob trying to talk to each other. But then she says, Bob is worried that in the quantum world, how can you be sure what you're doing makes sense? How is it that you even know? And there is a little evil character, Eve, that's what they call it, trying to snoop in on that conversation. So let me quickly show you how one would go about doing this. So classical channels, standard telephone lines, if somebody taps into your telephone lines, there's no way for us to figure out that there's somebody else listening on you. Right? Not possible. It just doesn't work that way. In the quantum world, of course, if you just add a quantum channel, so now since Alice and Bob are trying to put this new quantum infrastructure in place, they understand what it is. Even if you have Eve, who has a PhD in quantum physics, and she also has access to the same amount of infrastructure that Alice and Bob has, even then, Alice and Bob can figure out the presence of Eve, and that is going to help them make that channel secure. And that is based on very simple properties of polarization that we talked about. So let me just briefly mention to you what happens. I have two axes here where we were talking about just vertical and horizontal directions for the electric field oscillations. That's like, kind of like having an axis like that and measuring a polarization of, let's say, my little tongue here, which is holding here. Right? And think about a light shining from the top, and then you will have a shadow. The shadow will have a certain length. That will be that will be like measuring the off state, for example. And if you have light coming in from this side, shadow will fall on the vertical axis, and the length of that would be like the probability of being in the one state. So if you measure this state, it's going to be either 0 or 1 with the probabilities that are given by the lengths of these. Okay? But that's not the only way to do measurement. Who decides I need to measure horizontal and vertical? I could do that measurement at a diagonal axis like this. Okay, so I'm going to try to do this. So I have a 45 degrees measured like this, and then measured from here 135 degrees, another sort of measurement device. And I can choose that as my sort of a basis. And then the projections, which are on these different four axes, are going to be different. And that uncertainty of your quantum system behaving the way it's measured is what allows Eve and Bob and Alice, rather, to figure out the presence of Eve. So let's see how this works quickly. So in the information world, you send everything as bits, 0 and 1. So that's the message that Alice wants to send. Let's say instead of sending these bits over the telephone line, she's sending them as polarization. So vertical, diagonal, horizontal, like that. And each one of them have these specific values. Bob has the random choice. Alice may choose any one of these bases to prepare her state, and Bob is randomly going to choose one of these bases as his measurement device. Whether they agree or not, they have to verify that over the standard telephone line. Only when their coordinates agree, their values are going to agree, because now we're talking about two quantum measurements. If the quantum measurements are different, you're going to get different answers. That's just garbage. If the measurement axes are the same, they're going to get same values, and that is something that they can keep. So they roughly lose about 50% of these bits. Whatever is remaining is called the distilled secret key. Nobody else knows about it, and they can use that as a technique for coding their messages, as the basic key to code their messages. Now, what if Eve is present? The moment Eve comes in, she is going to do some quantum measurements, so she's going to mess up what Alice was trying to send in the process of that measurement, and then the survival rate of these bits goes down from 50% to 25%. And so Alice and Bob, all they have to do is verify when they're doing their first dry run to see how many of these bits survive. If it is less than 50%, they know Eve is present, somebody is listening on them, and they have to go up, figure it out, and make sure the channel is secure. So that's what quantum mechanics allows you to, and it is essentially just based on the uncertainty and the quantum measurement changing your state. Okay. Let's now talk about another very interesting property of quantum states, and you already saw a flavor of that, these superpositions that give you this very interesting bright and dark interference fringes. If we extend that idea of superposition to multiple systems, we get these so-called spooky quantum states. So it's kind of like this. You have two, so it's kind of like family members that have prepared in some initial state to begin with. Even if you now move them millions of miles apart, because they shared this quantum correlation to begin with, it allows them to hold these quantum correlations, unless, of course, something else can go wrong. And this has been, for example, illustrated for photons, which are light particles, for about 500 kilometers or so. So for about 300 miles, we have been able to develop quantum infrastructure where this entanglement survives, meaning you start the system here, prepare this very interesting state of two quantum system, one quantum coin given to Alice, other one to Bob, and they could be about 500 kilometers apart, and you get this. And here's just how one would write that quantum state down. It just shows two possibilities, like superposition we talked about, but each state now has two particles, and the way it is designed is if first one is carrying the stick pointing up, the other one is carrying a stick pointing down, or if the first one is carrying the stick pointing down, the second particle is carrying a stick that's pointing up. Which one it is, we don't know, because remember, if you measure the first one, it could give you either this result or that result, which is either up or down. So by themselves, each particles individually are completely independent. 50% of the time, stick pointing up, 50% of the time, stick pointing down. But when you measure one, you know immediately about the presence of the other one, even if the other one is now on the moon. Right? That's the interesting part of these spookiness of these systems. It turns out it is almost like action at a distance. It's like instantaneously they communicated with each other without talking over the cell phone. And that is something that perplexed Einstein for quite some time. There was a lot of debate about this. The debate, of course, now is settled lots of technologically advanced experiments. We understand quantum mechanics, and it tells you that you can have, the term that is used is non-local, things that are not at the same place, really far away from each other, but are correlated with each other. This is something which has no analog in classical world. And that one can then take advantage of these ideas. So if you observe one here, you are immediately, instantaneously affecting something that is tremendously far away. How do they do that in the lab? Dr. Wong, for example, who is in the audience, I think, has this interesting looking BBO crystal. You shine an ultraviolet photon on it, out comes two photons, and these photons come out in cones, and this is just kind of a false color illustration of it, if you will. Where these two cones intersect, here you get these entangled states. You don't know whether it's horizontally polarized like this, or vertically polarized. You could have first one horizontal, second one vertical, or the other way around, and that allows you to use that state, and that state can be used then for a variety of interesting things. Quickly, in 2 minutes, I want to show you one very intriguing and interesting use of that, and it's called quantum teleportation. I'm sure all of you have heard of teleportation. Quite a few of you must have seen Star Trek, right? So I'm sure all of you are fascinated by the idea of teleportation, as I am. At least for now, it's not possible for classical objects. We can't teleport. I would like to go, my kids would like to get teleported to India every day for their dinner if they could, right? But we can't do that. But at least for quantum states, we can do this. And this is very interesting, experimentally achieved, so not science fiction. So what's going on here is we create an entangled pair that is shared between Alice and Bob. Okay, so one is with Alice, the other one is with Bob. And there is some initial state that Alice wants to transport to Bob, which he may be really far away. Now remember, this is a quantum system that we don't know what it is. Alice cannot do a measurement. If she knew the measurement, if she could do the measurement on it, she could just call on the standard phone line and tell Bob, okay, this is the system we're talking about. That doesn't work. You do one measurement on it, your system is disturbed. You can't really do that. So she doesn't really have the luxury to know what she's transporting. And so what she does instead is she takes this, one of the entangled members, does a combined measurement on it, and because you have now 2 coins, you get 4 possibilities, right? 2 heads, 2 tails, 1 head, 1 tail, or the first one tail and the other one head. 4 possibilities. She communicates that to Bob through a standard telephone channel, if you will. And then based on that, Bob does 1 out of 4 transformations on the other entangled member that he shared. And the initial state, which we did not know what it was, gets teleported to where Bob is. Okay, so just by communicating over a standard telephone line, and of course having this quantum infrastructure, if you will, to be able to share quantum entangled state, you can do that. So this is kind of like a fax machine that we are familiar with, but imagine once you send the fax, your original is destroyed. That's kind of what happens here. The original quantum state that you are trying to transport to a faraway location is gone forever, and you don't know what it is, even after transporting. So this very entanglement is thought to be something that birds and other animals use. Migratory birds, for example, they navigate using Earth's magnetic field. So to get on their long migratory journeys, they need to track Earth's magnetic field. And it turns out the way their vision works, it uses the concept of entanglement. So there is some study that has been done on that. It is also, there is a very recent study that says our human mind, the way it processes information, also may be inherently based on entanglement of molecules inside our brains. And same thing with birds. For the birds, it is a couple of molecules in their eyes, how they react to the absorption of light. So there is actually vision of the birds is governed by this quantum entanglement. So again, very interesting areas, very interesting applications of this. Where are we going with all this? Quantum computing, that's kind of the ultimate frontier, if you will. Here is how real quantum computers work. That's just a cartoon, and physicists like cartoons. If a physicist is studying cow, we would study a spherical cow first. A simpler system, so you can understand what's going on. And so here's an isolated quantum system inside that sphere, and some connections coming out so that you can do measurements on it. Here's how a real quantum computer works. IBM's quantum computer, how many bits? Just 5 bits for now it has, and room full of stuff. If you remember old classical computers, they used to occupy a whole room full of stuff. And you see these cryogenic things. In the beginning, I showed you superconductivity by cooling these little pucks to liquid nitrogen temperatures. Here they use liquid helium to cool down even further. They use superconductivity, so these are superconducting circuits that you can see here, and lots of interconnections that you can see. This is sitting at the bottom here, and all of this assembly is sitting inside of this cylinder that you see here, which is which is cooled using liquid helium. Now, interesting thing about this is it's online, so I could log into IBM's computers and try to do a little calculation on their quantum computer, which just has 5 bits. So you can't really do much about it, much with it right now. At least, my recent paper that I'm working on, I did a little simulation of it on their computer, and then of course, it works the way it is supposed to, but only 5 bits. So you can't really do much with it as of now. I showed you another competing company called Rigetti. They have 8-bit quantum computer. So that's kind of the ultimate frontier. And we are almost there. We're almost there. So here's just a quick review of what we did. We studied that quantum systems have quantized properties. Energy, for example, cannot be exchanged in continuous chunks. You can have quantum objects in 2 states at a time, schizophrenic. You can have superpositions of multiple systems that are highly correlated, even if they are farther away, entanglement, and that may be how our brains work. We have already seen evidence for the brains of birds to understand how they navigate through this. So here's about a dozen quantum science and technologies that have come about in the last 4 or 5 years, if you will. Quantum simulations is something very interesting. Nowadays, we use classical computers to simulate how chemistry works, how drug discovery works. So we're trying, and at the basic foundation of it, these are quantum systems. Atoms behave quantum manner. You couple them together. Molecules are quantum objects. You're trying to simulate a quantum system on a classical computer. It's not very efficient. It takes up a lot of energy. We can't solve problems that we would like to solve. So drug discovery of future will be done through quantum simulation, for example, just to kind of give you an idea. You have heard about artificial intelligence, machine learning. Even in the classical domain, we just kind of try to understand how all of this works. The quantum community is already on the go, and they have developed protocols for doing quantum machine learning, quantum artificial intelligence, if you will. Myself, I have been fortunate to work on several of these areas that are listed here. Quantum teleportation, which I talked about. Quantum metrology is something I'm working on right now. So thank you very much for your time and patience. And here's a little cartoon that I'm going to leave you with. The elderly people in the audience, myself included, you need to understand quantum physics, because like the cartoon says, 1 in 3 kids will experiment with quantum physics. So you need to understand what's going on. And it's kind of a little goofy cartoon here. The mom says, I'm not angry, I just want to know where you got these LHC, the Large Hadron Collider, the big experiment in Europe that was very successful a couple of years ago, data graph. So the father is asking son, how long have you been calculating these quantum cryptography formulas? I gave you a little flavor of quantum cryptography, if you will, the quantum key distribution idea that we talked about. And mom and dad are arguing, oh, your daughter was doing the double slit experiment. You remember the interference experiment that I showed you on our bed again? And so they are kind of worried about it. That's it from my side. Thank you very much again for your attention. I hope you got some flavor of what is it all about and all the fun things that you can do with it.